We'll start off here talking a little bit about the threat that large loads pose to the power system. And in my world, especially recently, I've been working on a lot of integrated resource plans where utilities and utility commissions all have these very optimistic forecasts regarding the amount of large load they're going to bring onto the grid. A recent report from the Department of Energy forecasts 12 gigawatts of data center load to come onto the non-CAISO West. So that's, Alberta feels reminiscent to Utah. It's a big place with not a lot of cities. So 12 gigawatts feels like a ton. And one of the things that we want to highlight here is as we look ahead to, we forecast this increased loss of load expectation, how do system planners approach the combination of large loads, extreme weather, and the retirement of firm generation resources? We've seen in recent years some pullback on those commitments. I believe APS down in Arizona just recently pulled back on their commitment to be 100% clean by 2050, and that is just a reflection of the challenges that some of these utilities are facing with regards to large loads. One of the things that is a best practice in planning, although difficult to implement, the utility space being a relatively conservative, slow-moving beast, is something called round-trip planning. So this is something that we think about a lot in terms of when we support particularly utility clients. When utilities are planning their system, they have typically 20-year long-term capacity expansion models, and they'll evaluate those models with different load forecasts, different resource candidate options. They'll take the resulting portfolios, plug them into a production cost model, so that might be Plexos, that might be GridView, that might be maybe an open source tool to actually dispatch those resources and evaluate, okay, I have this quote unquote optimal portfolio, how would it dispatch to serve load? And then the last couple of steps, which are the steps that are typically hardest to implement, is taking the resulting portfolios that you then ran through a dispatch and conducting a stochastic resource adequacy study and using that last step to evaluate, okay, is my portfolio going to be sufficient to meet my load growth trajectory and all of the constraints I might have? So I bring this all up to say it's a difficult problem, right? So I'm going to talk here a little bit about how we deal with extreme weather events in load forecasting. And the extreme weather is a component, much like large loads, that is getting talked about more and more. I asked a couple of questions yesterday in the session about, how do you deal with extreme weather to other panelists? How do you think about frequency? How do you think about magnitude? It's very challenging, even with relatively large weather records, to forecast conditions that we've never seen. And we'll talk a little bit more, but in a couple of slides, but extreme weather and extreme loads usually fall far outside expectations, so whether that's 1 in 2 or 1 in 10 type loads. And utilities are just not going to be able to plan to those conditions without taking a really hard look at what extreme weather could do to their system. The FERC, on one hand, so we'll talk about transmission planning as an example for this methodology that I'm going to introduce. FERC recently, updated FERC Order 1920, and that is an order to require regional transmission bodies to consider multi-benefit categories for transmission planning. So that means instead of just doing reduction in production costs or reliability studies, you need to also consider these holistic benefits, which key to that is the mitigation of extreme weather events. I'll mention the reason this came up for us at Energy Strategies is because we have clients, primarily transmission developers or folks that are trying to pitch transmission development, that want to get a holistic look at the benefits that those transmission projects would provide to the system. And one of the topics that's the most difficult to capture is the influence of extreme weather. And it's relevant here because as this study, this is a Lawrence Berkeley National Lab, and just for orientation here, those vertical bars all represent individual transmission lines, and the height of the bar indicates the percentage of economic benefit realized from just 5% of the hours in this 8760 study. So the takeaway here is, for most of these transmission lines that they studied, most of the benefits for a particularly transmission expansion candidate accrued in a very short window of time. That short window of time is very likely related to some anomalous operating condition that the pre-expansion system could not handle appropriately. So these extreme weather events are difficult to capture. We know that we need more transmission expansion and interregional transmission. And when you build those lines for those conditions, you can expect a lot of benefits. So what we have worked on and we've used for a couple of projects is what I call this extreme weather informed load forecasting approach. Clients would come to us and say, hey, we are considering a transmission expansion candidate, and the WEC heat stress test from the 2032 ADS is good, but we actually want to test the condition of what would have happened if we experienced Winter Storm Uri or the 2021 heat dome. How would this transmission line have helped in 2030, in the future, right? Because it's going to take 10 years to build a transmission line if we were to experience an extreme weather condition that we are familiar with. This is really important for us as consultants because, well, I think it's important for everyone. Everything you do, you're telling a story to try and convince people. So for these clients especially, they want to be able to tell the people, their audience, hey, remember that storm that was really tough for our system, that was really stressful? We're going to replicate those conditions in the future so that we can evaluate the benefits of this transmission candidate. And that's a really salient way to have a conversation about transmission expansion, which is like super tricky to do in a quote unquote optimal way. So looking at this model, we're right now using FERC 714 data, which is nice and is relatively long. It runs about 20 years. The spatial resolution is not very good, so we'll say that more data is always better. I think a lot of folks talked about that yesterday. But we evaluate each week in the historical record for its deviation from expectation, meaning like how anomalous was this week's net load profile relative to the expectation for that month. And we say, okay, this is an extreme weather, or this is an extreme week. And it's helpful to be able to connect that extreme week that you find empirically with something from the weather record, which we typically can do. We can say like, oh, this week in January 2024, that was actually the polar vortex in the Pacific Northwest. So great, good story there. So those conditions, that shape, we do some kind of a normalization and rescaling, and then we have a simple optimization algorithm to get the load shape forward cast into what is typically used for a planning study, which is something like the WEC ADS or the WEC anchor data set out into 2032. So this gives planners the opportunity to experience the extreme weather condition within the context of their existing planning studies. Thank you, yeah. And here's just an example of what it looks like. This red figure, and I sort of skipped over this, but it's really important to capture the coherent weather-dependent generation resources and fuel prices, because those are really critical components of reliability, especially when things get tough. But that figure up on the top shows the extreme weather event, or the extreme weather event profile forwardcast out to 2032 compared to what's in the WEC ADS. And I show this, well, one, to show the results of this approach, but two, oftentimes, or previous to this approach, we would just sort of simply scale up the load by some factor, 100%, 20%, but that doesn't necessarily capture the shape of the extreme load. And oftentimes, extreme weather conditions are even more extreme than you might imagine. And the extent of those, because we do this on the WEC level, not just for a single utility, the extent of those weather conditions is going to be really, really critical to evaluating how a transmission expansion can benefit your system, right? And I'll just leave off with a couple slides here to illustrate that if you're basing your planning studies on a single weather year, you're not going to get enough data to accurately represent the future asset life of the investment that you're considering. So 40 years, 60 years. If you're relying on a single base weather year, you're not going to get all of the weather conditions that you should expect. And that's really important in terms of calculating the economic benefits over a 40-year lifespan. You need to feel reasonably confident that you're reflecting the history so that you can make those investments with confidence. So the next steps for us in this effort is building something called a synthetic weather year, where we are taking 20 years of data and constructing a representative 8760 that captures median, extreme, and non-extreme conditions in a single 8760, but one that is representative of the last 20 years of weather. And that's it for me, y'all. Thank you so much for the time.
So I'm going to give my perspective from the point of view of a computer scientist. And I'm just looking at this project and generally working in this area of the grid. Is kind of an extremely data-intensive, transdisciplinary activity where people have expertise in kind of weather, climate, atmospheric events, electrical engineering, new materials, and so on. And how can we build an infrastructure that can help people make decisions and with good quality data, with the proper support of the latest technology, and so on. And so kind of in my mind is like, how can we build a cyber infrastructure that can unleash the human intelligence or the human expertise with all the support of easy access to data and the latest advances in artificial intelligence. So the first aspect is how can we build a cyber infrastructure, and this is something that we have been doing in the WIRE project, leveraging a lot of the work also started before from the National Science Data Fabric, with a few pillars in terms of being able to access data easily, collect requirements from the user communities, and basically making sure that as we develop the infrastructure, we don't do just things that are cool from a CS point of view, but really something that is useful in practice. How we can integrate those tools and make it useful for the scientists. But then there is a lot of questions in terms of the cost and effectiveness of the infrastructure. How can we make sure that people don't have to pay a lot for using cloud resources? How can integrate the AI tools? How can they connect live experiments with the simulations that is happening on a different site? So generally speaking, we're looking at leveraging an infrastructure that is actually foundationally designed for attacking many different disciplines. And then in this case, we kind of narrow down on the aspects that are particularly useful for this community. So working with people here, we look at also how we can make simulations in terms of predicting the load on the power grid. Some people are looking at how to use solar panels, is that the smoke is going to affect them, the weather, and so on. Now, how can the core infrastructure be connected to kind of many other data sources? And so, for example, we have been working with data from NASA and NCAR and other centers that deal with weather and climate data so that we can actually get short-term, long-term assessment use of the data. And for example, we have like 4 petabytes of data from NASA that some of the people are using internally, but also we have like a community data challenge. How can that be used? How the analytics can be done? So for example, actually early this week I was visiting NCAR and they were doing a training for people locally, and we connected with their resources. And now their data from our cyber infrastructure is available online. So here is pointing on some of the dashboards that are available actually in real time. And through the WIRE and SDF websites, people can connect to that and maybe use your Python environments. We're targeting Python mostly just because it's easy, but that people can use it in their simulations. Similar, we are taking data from the University of British Columbia. They had those short-term smoke prediction for a couple of days, and actually we compile a large sequence of those, and now we have like a 3-year smoke data sets over US and Canada, and that can be used by many people for designing long-term activities and things like that. So generally speaking, the issue is that taking those data collection and make it easily available and usable, even if they initially were designed for different purposes, and also building the infrastructure that makes the accessible for everybody. Similarly, like when you build your power grid using more advanced materials, new materials and so on can be a key aspect. And so we have actually a deployment on the Cornell synchronous light source. And now if people go and do an experiment there, we can actually make the data available immediately to people that maybe do the simulation and show different conditions for using that type of information. So this is kind of the deployment at CHESS, so people can go there, collect the data, collaborate externally with people, and generally kind of in a matter of a few days can get feedback in a distributed team and provide the results to the community. So this is kind of a type of resource that normally is not immediately available, that takes months or years to the type data of this type to be available, and now we can actually make it accessible in real time for different conditions. Similarly, from the engineering process, now we have done some experiments in connection with autonomous labs. And just as a demonstration, we did some tests with a few labs that are deployed at Oak Ridge National Laboratory. And something that typically was completely disconnected from the rest of the scientific community. Now we have done experiments that in real time make the data available, and people can give feedback, try different conditions, and use their infrastructure for that. And this one actually we're also getting better and deploying them quickly. So we went from a first meeting, it was like mid-January, to make a live experiment in real time by May with the whole infrastructure connected with the rest of the activities that we can work. So there is a kind of a shift to doing this only long term. Now we can do it kind of in the aspect of quick deployment of new capability for the community. So overall, basically, the idea is to have a different level of connectivity in different community and different environments. And so this allows people, like for example, think about the talk you just seen, how people make assessment, long-term planning, or maybe react to an extreme condition, and you want to have good data determining what's happening, if things are heating up, and so on, and to have a framework where you get immediately access to good data. The question is, on one side, how to make it efficient, but also how to make it affordable. Many have been working like for more kind of high-end cloud resources like Amazon, Google, and so on. And unfortunately, they have a price model that can be very taxing. Anything you do, API call, data streaming, egress, and so on, make things extremely expensive. And so some of those things could work in principle. Practically, they become impossible to use. And so we have been looking at kind of the jungle of pricing models. And in fact, they never tell you, it's never possible to be told, I want to engage in this activity, tell me in advance how much does it cost. And they tell you, well, you will see when the bill comes through. That's not ideal for a project. So we are looking at alternative activities. 2 minutes, right? Alternative activities, for example, looking here, it's trends in the climate temperature over 100 years, actually 140 years, and now streaming all this data through our model, so we can actually modulate the quality of the data, the amount of data you move versus the quality of the results. And if, for example, instead of using brute force everything, you can even modulate, say, oh, I accept an error of 0.01, maybe the cost of my analytics goes from $100,000 to $1,000 and even $2 if I'm teaching a class, I tolerate more error. So there is a spectrum of things that can be done to make sure that the work is doable also in practice within the quality constraints that the science require. And finally, one important aspect that is kind of emerging more aggressively today is that how can we make sure that industry, research, academia, and nonprofit, they can work together. And often their requirements, more in terms of policies, protection of the data, are very difficult. And so we have been looking at deployment of federated learning techniques where people can share models without sharing data, and that makes it much easier for especially industry. People have data of high value, they're now willing to put on the web, still work together and share results, do the science together, get the prediction, and work on those. There are challenges in terms of making those things available, in terms of the balancing of the data in different sites, how to transfer the data, and so on. But now this is being used effectively in different disciplines, predicting routes. We are using this also in medicine. There they have a lot of issue of protecting privacy and so on. And so this is really ready for fruition. And so assumption where it's difficult to collaborate can be actually overcome in the near future, and we're open to discuss with people. So overall, kind of from our perspective, is like we would really want to build an infrastructure that make it easy for people to analyze, react to extreme situation quickly, or make long-term planning, and effectively work together in the best possible way. Thank you very much.
Hi, everyone. I'm Andrew Wilson, as John said. I got in late last night, so haven't had a chance to meet any of you yet, but excited to do that today. My team at Guidehouse partners with utilities to use utility asset data and projected climate data to develop ground-up, data-driven climate risk assessments and climate resilience plans. So the first step in this process is to accurately quantify the risk on the system, both current and future. We focus on climate risk, as I said, and we use that projected climate data and asset data to develop asset fragility models that give us asset-specific failure rates out into the future. From there, we combine those asset failure rates with utility criticality data to quantify that risk in a financial sense, which can then feed into a benefit cost analysis as utilities consider mitigative actions. And I think the key point here is that using this data-driven, asset-specific, bottom-up approach has actually been shown to have a good support from regulators and led to far easier approval. Now, in this era of big data and AI, one of the phrases that you kind of hear all the time is garbage in, garbage out, and that certainly applies to this as well. There are two key inputs to our approach, the climate data and the utility asset data. Now, climate data is a potential pitfall. Basically all projected climate data, and this may be familiar to some of you or brand new to others, traces its way back to the Coupled Model Intercomparison Project, or CMIP. CMIP data is what underpins all of those several hundred-page IPCC assessments that come out every 5 to 7 years. Raw CMIP output, though, is coarse. That's one of the big challenges with it. CMIP models are huge and incredibly expensive to run, and so they're typically run on a 1-degree grid, which is equivalent to about 100 kilometers at the equator. Now, that's far too coarse for utilities to get anything specific about their territory or their assets. And so what needs to happen is that output needs to be downscaled. And in the last 10 or 15 years, there's been pretty incredible progress on that downscaling step by incorporating modern data analysis techniques and machine learning. Down here at the bottom, I've shown kind of what the difference is. On the left is a 1-degree ocean, and on the right is a 1/12 of a degree ocean. And you can see how crucial resolution is to really localized geographies. I'm cheating a bit. That's actually just a high-resolution model, but the same concept applies when you're thinking about weather data over land. Now, granularity is so critical for this, especially for something like flooding, where 10 meters can mean the difference between an asset being destroyed or being totally safe. And unfortunately, what I've found is that climate data is a place where utilities often want to cut corners, and I think I would just really caution against that. Ultimately, what this climate data gives us is hazard probabilities. So out into the future, in a given year, we get probability curves that say what is the probability of a certain wind speed. And that's how we get those 1 in 100 year events out into the future. The other input is asset data, which is just as important as climate data. And what we do is we use utility asset data to distinguish between assets on fragility or costs. And this all feeds into our CHARM model, climate hazard asset risk mitigation. And what the utility data does is it gives us nuance, and it lets us do an asset level, asset specific analysis. So for each asset out into the future, what is the probability that a given asset fails in a given year? From there, then that better data gives us a more granular risk assessment, and that more nuanced risk assessment can then lead to more targeted like resilience plans and mitigation decisions. So far, this has been a bit high level, I would say. So what we really want to know is this: what is the probability of failure in a given year? That's what a utility wants to know. And there's a few ways to do this. For those of you who are plugged into EPRI, you'll know that they've been doing quite a bit recently on fragility curves. And that's effectively a probabilistic view of asset fragility in the future. And you combine that with the hazard curve, which we get from the climate data, and you can then get a probability of failure for an asset in a given year. So far, fragility curves have been fairly, I would say, limited in the type of asset that they're available for. So there's quite a bit for wood poles, some for wood poles exposed to wind mainly, some for transmission towers, and then it starts to really become a little bit harder to find. But those wood pole models are ultimately, at the bottom, physical models. It's some structural model where there's a Monte Carlo simulation that gives you this probability distribution. If that fragility curve isn't available, you can also use some of your own physical models. Guidehouse has an internal model for transformer heat degradation, accelerated aging effectively, which gives us basically how a transformer is going to respond to a chronic risk increase of extreme heat. But sometimes even that's not available, and then you have to go to those more statistical models. And one thing that we've seen, or starting to see more and more, is utilities developing their own ML outage prediction models based on historical outage data. I think one of the places that I'm really excited for moving forward, that I think we're going to start to see more and more, especially in the coming years, is physics-informed ML models. Most of what we've seen from utilities so far is purely statistical, but those could definitely be improved by including some kind of physical model into that. Now, obviously, risk quantification is just the start. The next step is understanding what to do with that information, and as I said before, those mitigation actions. The benefit of our CHARM model is that we can effectively plug in a proposed asset upgrade, protection, modification, and then rerun that risk model out into the future to understand how utility risk, both asset risk and financial risk, changes over time. And that allows utilities to do very specific and targeted resilience plans and adaptive actions. I've hustled through this a little bit because I think so far I've been a consultant, been pitching a little bit, but I'm really excited for this panel. And one of the things that I would love to hear from the other panelists and from all of you today is kind of how you think AI and ML can improve this process and grid resiliency in general. I'm very close to risk quantification and risk assessment, and so that's where I'm very excited. My background is actually in academic research and climate modeling, and so climate data is a place that I'm hugely excited for what comes next. AI-driven downscaling is going to make it's only getting better. It seems like every few years another climate data startup comes out with more granular data than we've ever seen before. And then the other place that I'm really excited is those compound hazards. So compound hazards are what's super impactful for utilities, and unfortunately is a bit of a weak point right now for climate data. There's a lot of uncertainty in things like an ice storm combined with wind. But that is what's so dangerous, and that's one of the places that I think in the coming years there's going to be a lot of progress made using some of these new AI tools. Now, all of you who are familiar with utility data will know that it, I think the nice way to put it is has its limitations or is challenging at times. And I think that the other place that I'm really excited for is how modern AI can improve data collection, correction, or augmentation in some way. So things like quicker asset inspections with maybe AI-enabled drones that can get you data quickly. Sure. Or even, as I said, data augmentation. So looking at past outage data, I think one of the problems and challenges that we see is often these events are very rare. And so in an outage management system, there's very few examples of this happening, but with the rise of generative AI, there could be some kind of data augmentation where we can use AI to kind of generate more samples to then make decisions off of. So that's kind of all I have. As I said, I wanted to keep it brief so that we have some more time for questions, but thank you all for having me here today.
Good morning. I'll also try to keep it brief here. We've heard some great comments on grid resilience. And I think the biggest thing about use of data in AI is that they're a means to an end. They need to be actionable at all times in the context of these different grid resilience problems we are talking about. And how are they being used today? We see a lot of use of predictive risk monitoring, early warning systems for ignitions, for climate risks, like we heard, weather risk, asset failure risks. These are the type of risks that come in and can be improved by data and AI. Similarly, grid-aware situational awareness, like anomaly detection, dynamic topology adjustments that is very difficult right now, and quality monitoring of the assets and systems. And then resilience planning, right? Scenario development, prioritization of investments toward resilience, and then resilience co-pilots, so to say, to drive these prioritizations and scenarios. And then if you think of AI integrated decision support and resource coordination as sort of two parts of decisions that are being made. Microgrid management, for instance, DERs or demand response is a part of it, right? And then for decision support, it's really important to have that concept of incidents that can happen. For instance, wildfires is one of them, of course, but it could be also attacks, for instance, on the grid. So these requires also decision co-pilots that actually understands the situation through data and AI holistically, and maybe assist the users in these dynamically arranging and changing situations, and workforce training based on those scenarios related to it, and then explaining those decisions that are being made to the public, their interpretability of the risk and also explainability of those decisions. Those are all opportunities for data and AI, and we've been working with some of the stakeholders in this area. All of these requires data, but data is only a part of it. Data is, at best, something we can put into these systems, but best of science and AI models that are happening today isn't going into operational systems. So we need to learn to expose models and AIs also just like data, and build services as an ecosystem for them to be exposed and be useful in a almost like this marketplace-like setting that also then be actionable in the context of solutions and also collaborations. Lack of standards, too much value, too much data or models that are coming up in the research circles, at least, without a lot of value generation from them. Quality, the processes for acquiring these models. There are lots of different issues here, right? And culture towards one size fits all instead of using the right tool, right model, right service at the right time. And like this reliance on often closed box solutions because we didn't know any better before. But now we can actually embrace open data and open models in a risk-aware fashion. There are some things that don't have to be at all times closed. So I'm sorry, I'm having a little hard time going here. Maybe I should have my mouse there, right? Okay. I didn't notice the flies weren't, they're advancing here, so. Okay. So this is very complex, right? And we need to make the complex simple. There are ways that we can do this. There are collaborative models that are emerging, integration of domains, technical and community expertise, and co-design, co-production as multi-sector partners, and also use of data, AI, computing in a very composable fashion, in modular fashion, that we can actually use the right thing for the right task and integrate these solutions together. Actually, I lead a new lab that we formed everything that was mentioned about me actually under one umbrella called Societal Computing and Innovation Lab here. Because we noticed this area, grid resilience, for instance, is an area that affects the society a lot. So our solutions actually touch in the innovation landscape in a very different way. It's very science integrated. It's very data integrated. And how do you capture science and data in knowledge systems so they actually derive these, what we refer to as digital twins and complex systems around them? So how do we put all of it together? There's an innovation model here, right? We need to understand what problem we are solving so we can target the right thing. So if we put the right data and knowledge and models, service-oriented systems together, we can actually create innovation pathways towards them and start integrating solutions as minimum viable products that we can create partnerships to scale and sustain them over time. We actually have been using this approach over the last decade and a half in different spaces, starting with wildfire. So we are turning those and using these current areas in data and AI in integrated research workflows, composable systems, data and knowledge systems, and applying more agentic ways of bringing them together within digital twins. So there's a huge area, I think, that the Wired Center can make a big impact because we are here as a cross-sector, cross-national community, and we can maybe develop those solutions in ways that scale and sustain into the future. So this is an example with SDG&E, what happens when you start opening those pockets of possible data. Right? In SDG&E, our collaboration here, there's a movie. I don't know if it's going to play. Let's see if it does. Sometimes from Mac to PC it doesn't, but you're seeing a movie here. It shows outage prediction that are vegetation related. So there's vegetation data, there's weather data that's open, leading to vegetation failures that lead to then grid outages. And the blue lines that you're seeing pop up, I'll play it again. See, the video isn't showing there, it's showing here, but somehow it's not there. Maybe like that? Okay, now I think it's gonna play. So what we are seeing is model predicted red areas based on vegetation and weather conditions leading to those red spots. And then the blue that you're seeing is public safety power shutdowns. And under those, once in a while, you'll see those black dots that are real incidents of vegetation-related outages. So what this means is we can now put the data together from vegetation and weather, create models to predict those, and using those real-time outages that happen. But then we can also overlay with SDG&E these PSPSs to understand their effectivity. Why is this important? If we didn't start putting those data sets together, even within the utility, it's really hard to collaborate within vegetation and threat, like wildfire threat, safety, divisions. So we were able to actually change some things about how that collaboration happens just by showing some of these integrations together. So slowly, I think we can go from more traditional ways of managing I'm having a hard time with my, okay. So traditional ways of managing our data and service infrastructure to integrate it more open data-oriented ones. And we are, over the last couple of years, we've been building an environment called Wildfire Commons. So we are building 3 things in the commons to expose these data and models that are useful. One is an expert network. So we are bringing a cross-sector community as a knowledge graph of expertise, what others can provide. And then we also are building a platform called Fireforge to catalog and build service-based solutions through a cloud-compatible platform. And then coming soon in December, we are about to announce a marketplace based around collaboration and exchange of these solutions so they can help each other sustain. What this means is we can now start engaging with communities like the Wired community. We have working groups and things like that, but Pathfinders are a way to bring community in to the Wildfire Commons. If you go there, you can log in and make yourself actually a part of the expert network and start using the Fireforge. We are also hoping to create a data challenge together. And Fireforge within the Commons is powered by a National Science Foundation project called the National Data Platform, and the data challenges are run through it. So what we are going to be announcing in fall this year is a Wired Center Grid Resilience Data Challenge. The timeline will be from December through April. We'll have a problem defined by our grid partners. We'll reach out to you, and please reach out to us if we don't, on what kind of problems you'd like to tackle through a challenge like this around what data. And then it's going to be open to all students across US and Canada. And finalists will be invited to a weekend in San Diego, and we hope to select some of these finalists as our summer fellows for Wired Center next summer. And as I mentioned, this is an already ongoing platform. We in the National Data Platform built a service ecosystem for those solutions to come together. And one of those solutions that's coming together that the Data Challenge will run through is this, we call it an AI workflow engine for education. So there are collaboration studios that students can collaboratively work through. They can share their workspaces, that they're bringing data models from catalog, and they can compute on national compute while they're doing it, along with things like private clouds like Amazon or on-prem computers. And if you go to the National Data Platform, you'll see an example one. You can just log into it with your ORCID. And Fire Ready Forest Data Challenge that ran last spring. And you'll see that there are some sprints that you can actually reproduce the work of, and the solutions that are winning are made available on the platform for other students and the community to learn from. So that's one thing that we hope to do with the Wired community, along with a Pathfinder, to bring some of the data sets into the catalogs of the Wildfire Commons with a special shell for Wired Center around it. And the other thing, if you're here, Hannah is sitting there, and Katie is sitting there, please talk to them about how some of these digital twin approaches can be dynamically brought in the Commons. The last thing I want to mention that, and I'm not going to talk about it, but are there risks to open data and models? This is what I get asked a lot. I think this is a situation where benefits outweigh the risks. So we really need to go problem-based. What's the user-inspired problem? What are the data sets we can expose so more people can be a solution, part of that solution to that problem? But we really need to understand at the data set level, model level, what would be the risk and how do we mitigate that? So these are actually through responsible data governance and working on a problem-based, we can, I think, mitigate these risks. Thank you.
Good morning, everyone. It's my pleasure to be here this morning and to talk to you about our data sets and our data challenge, and I'm going to provide some complementary viewpoint from some of my panelists. I've heard a lot from the universities, the industry, and I thought that it would be fair to say, oh, what about the national labs? So national labs, we have 17 in the US. We do research mostly on behalf of the US Department of Energy, and specifically with the Pacific Northwest National Lab. We are situated in the state of Washington, in Richland. We also have offices in Seattle, SQUIM for marine sciences, in Portland for a lot of the regulatory research, and also in DC for a lot of, where we evaluate a lot of the policies. The US Department of Energy is big. There are multiple offices, and so is PNNL. We are organized in a way where we respond to a number of our sponsors. On my side of the shop, we do applied energy, and on the energy environment, those are the different research area, and specifically what I'm going to talk about is electricity and energy infrastructure, and energy security and emergency response. So this is our approach to resilience. It really follows what my fellow panelists have been talking about, especially with climate resilience. We start with very large global change models. They are a mix of climate and economics balance models. We then need to go to a finer scale, so we have a lot of downscaling, but you still need to go to the extreme. So we use even more models to go to local scale extremes. You have heat waves and droughts, wildfires, floodings, and hurricanes. And then you need to translate them into impact onto the grid. With the, I think this is Brendan mentioning it yesterday, making sure that we're looking at the resource availability, the impact on the assets when we lose the assets, and then on the load. And then we can go and adapt, respond, recover, work on a number of the grid problems. So I'm going to talk about data sets that we develop, and then I'm going to talk about a little bit of this. I'm going to be a bit into the weeds, like if you're a student or you get your hands dirty on what it is to go and use AI. So first, some of our data sets. What we currently have, I don't know if it's, yes, it's running. Some of the climate data sets is actually one that Alex was mentioning earlier, is a data sets on climate where we address stakeholder concerns on, it's not about necessarily uncertainty in the future because we don't trust necessarily those uncertainty right now, but what if the heat dome for 2020 was happening in the future, what it would become? And we've developed and used those data sets. We transform them into load and temperature and power outage data sets. Here you can see it at the county scale. What is important is to have them at the scale that is relevant both for your constituent but also for the power system models. What we do have right now in terms of data sets is a catalog of heat waves, which is relevant for the NERC A96 reliability standard, actually it's NERC TPL08 standard. We also have those catalogs that are based on power outage, but also on load. And I'm going to talk a little bit more about that example later. Energy drought is something that was also presented yesterday on this map. You're going to see each circle is for a balancing authority. So this is where wind and solar needs to be balanced by regional resources before getting transmission studies. And the size of the circle is for the frequency, the color is for the duration. And something to see on this one is for the contemporary infrastructure. You have more energy droughts, renewable energy droughts on the east side of the western US. But the droughts are going to be longer in California, over 5 days. It's very important for understanding that paradigm between whether you need storage or when you should rely on transmission. So we have data sets of capacity, wind and solar that are gridded so that you can test all of your different infrastructure. I actually work a lot on the droughts. So here again, we're going from climate, more models, now you put it into the hydrology models, river routing, water management, hydropower, thermoelectric plants. just more and more models. The outcome of some of this modeling is that we have power system ready data sets for hydropower that are currently used for the WEC ADS. We did 2032, we just finished 2034. And even though this is for seasonal and long-term planning, when it comes to resilience and it comes to water, we also need to have a little bit more of hydraulics. So we also have data sets and models to understand what hydro can do to support resilience during an unplanned outage, for example. I was talking about catalogs. Here a bit more about catalogs. What you have on those maps are, again, this is by balancing authority. The circle is for the size of the generation. The color is for the severity of the droughts. And I'm showing 2 droughts. The first one that you see on your left is all brown. And if you were to rank your droughts, you would find that the first one on the left is the one that is the most severe. So this is the one where, for example, if you want to have reliability standards, it's like, yes, you want that one. But the one on the right is one that is number 2 or 3, or maybe that was 4. And you can see a little bit more of regional diversity. And so this is the point where when you're going to use AI in the future and you tell me, give me the worst drought to consider for my reliability standards, you really want to work with the expert. Because the one on the left is really going to really tell you about how much storage you need. But if you really want to look at your transmission, you should go for the drought that is on the right, because it's going to have that regional diversity. So that will be one of my redundant theme for this talk. Ask the expert. I know you have AI, but I think some of my panelists say it too. You do need to have the expert. On the wildfires, we also do a lot. Again, it's different models that we rely a bit more on a lot of observations. This is similar to something that Ilkay was showing. It's the potential based on vegetation, the potential of wildfire, and then we translate it into power grid stress. And we have a number of products that go from prevention and mitigation to what you do for the response, and then recovery and preparedness. So I'm not sure if you perceive here how many data sets they are. And then we have more. We have for floodings, we have for hurricanes, and I could go more. What I want to talk here is really what do we do about them? We expect AI to use and to find those data sets and assume that they are all evaluated and available and so on. And so the way that we've been proceeding with research is first with workflow. What's important is not in the workflow, it's actually a workflow that is similar to what Alex was showing. We go from climate to a lot of different models. We get to the load, we go into the grid. The point is that those workflows, they need to be documented with the different version. Each model needs to be evaluated. The input and the output of each of data sets need to be available to be fair, findable, accessible, interoperable, and reusable. So it's a lot of work. The other challenge that we have with data, besides storage, is this example that I have on the right is a different platform. Some of this research is developed under one sponsor, and so we have a supercomputer where we have 200 terabytes of storage, and we can do some computation. But then we move to a different sponsor for more applied work, and then we have to move to another platform. And so this is one of the challenges that we have in using AI and AI workflow, is that we, based on the sponsor and who is doing the research, we can't use the same, just one platform. This is my laundry list of things I need solution for, by the way. The other questions we had is how to make data available and findable. So we're doing a lot of detail and strategic metadata. We mint the data sets to make sure that people can find them. We are limited very often in the size of the data that we put out there. This is 2 gigabytes for Zenodo, for example. Well, with 2 gigabytes, we can't put our workflow. We can't put the input into the models and the output of the models and so on. It means that it will be up to the user to reconstruct everything. And that's also one of our challenge on how to create the metadata so that people can reconstruct all of those data sets. We are putting all of our individual data on a data portal. It's earthandenergy.pnl.gov. We have multiple themes. All the ones that I was presenting are already there. This is awesome. I know that a number of people have found it, so this was very nice. But those data sets, the issue is that we can only put fair data on it. But when you work with the industry, there's a lot that is protected. So it comes back to a little bit of a word of mouth. Please ask us. It's not because it's not on the catalog that we don't have it. We just need to work together. Same thing on how to provide data to support the industry. When they're on Zenodo or MSD Live, we provide the entire data sets, terabyte of data. Typically, the utility to develop reliability standards, for example, they don't want to gather everything. And so the last portion that is being used right now, and as an example with NERC, they're providing the catalog of heatwaves library. It's already processed. This is, it helps, but it's a little bit not transparent because I haven't seen the workflow, all detail, and so on. So I want to use it as an example for that heatwaves library where data are already all processed, but they are processed at the scale of the NERC region. However, the expectation is that each of the utilities within one NERC region is going to collaborate to see if this is the heat wave that they want to select for developing their reliability compliance and their the reliability standards. So it means that no matter what, the utility needs to go back to the raw data that I was presenting earlier so that they can do their own analysis. And this is a little bit unfair because each of the utility don't necessarily have the same resources. So what we're proposing is a GenAI GenAI Copilot assistant that is going to go through all of our data and could provide this information. I'll go a little bit faster. This GenAI here provide higher resolutions, provide the raw data. They provide at the county scale so that independent utility can look through it, and they provide more information. This is not just based on temperature, but also on load, power outage, and that provides the same information to all of the utilities. If you work typically with utilities, you would expect to go with our data, and we come back, see you next week, and then we provide you what your next catalog should be. With GenAI, people have an expectation that it will take you 30 seconds to have an answers. 30 seconds to go through our 40 terabyte of data is a little bit unrealistic. So we're being asked to do a lot of pre-processing of data. And that pre-processing is meaning that we have to go in the trade-off between what is really GenAI, what it's supposed to do, but for computational performance, we have to do a lot of the pre-processing. So what's the difference with a dashboard? So that will be a question that we have here for the tools is really making sure, what it takes to make data GenAI ready. For performance, and my takeaways here is that, we have a number of solutions, but the accessibility and usability of data remain a big area of research. As GenAI user, please request insurance on quality. That comes back to, I think, a comment Ilkay made. There is a risk of misinterpretation. You need to know which data was used. You need to have the entire provenance and the workflow, because else you could have data coming from different data sets that are completely inconsistent, and you have no insurance on the results. And strategic discussions between users, subject matter expert, data, software, hardware. The part that I didn't talk about here is that it's not just about the software and then the data management and the metadata, but it's also the hardware in the back. And so it's really a big team. So don't expect to do it alone. Thank you.
Questions teed up, but the questions that you all provided are sort of supersede those. So I'll turn those, we'll go through some of those. And again, if you still want to vote on any of those questions or put in additional questions, go to slido.com and put in Wired 2025. So something that crosses for all of the panelists. What concerns do you have about the use of AI in your area of expertise, and what could be done to address those concerns? Who wants to kick it off? Maybe it'll, yeah, you got to push up.
So one question that I've seen often emerging quickly when people start using AI and involves the domain experts is the issue of hallucinations. It's like when you adopt some tools, basically you need to have the community start testing the work without assuming that the models are actually doing the right thing, and to what degree they produce results that make sense, go back to the source, and so on. So in a way, maybe I would like to amplify the question from the domain expert's perspective, how much you feel you can engage in the process of testing if the AI is actually producing results without inventing things that don't make any sense.
I think, this is working. I was going to go a slightly different direction. I think one of the things that concerns me is just that there's a lot of using AI for the sake of using AI right now. Quite a few companies just think that it's this thing that you should apply to every problem that you have, and there's many cases where it's actually not right or not necessary. So for example, I was talking a lot about fragility models of assets. Like, physics is very good. We had hundreds of years of developing physics, and it's going to be faster than using an AI model and less expensive as well. So I think for me, it's just making sure that you're understanding the use case and where AI is good, where it's beneficial, and where it's just not necessary.
I'll build on that a little bit too. It's about the problem AI is being used to solve, and within the context of that problem, how we are actually using AI in a way that's interpretable, explainable, and really useful. So human AI collaboration definitely is a part of it as well. So we, as I mentioned in my talk, we had to build a whole approach for how to even bring stakeholders together who don't necessarily understand each other's perspective to define that problem so we can get to deploying AI in the context of that problem. So if you ask me about AI, the first thing I'll say is, what problem are you solving? There's a reason for that. And then there's, of course, the technical challenges in deployment of AI, as Valerio mentioned. You know, how do you actually make it trustworthy, responsible, interpretable, explainable, but then like in the context of that problem. Right?
I think about it from partially because I've been in front of a lot of regulatory commissions lately, thinking about it from the perspective of how do you build trust in AI-informed decision-making, either whether that's planning or operations. And AI, you know, to my panelist points, there's a lot of enthusiasm around AI, and there's going to be a lot of misappropriation of that solution. When you're talking to regulators who are by their very nature conservative and trying to maintain the one day in 10 LOLE, all that kind of stuff, AI is a little bit of a black box, and so until you can demonstrate a record of success using AI-informed tools, I think there's going to be a steep curve convincing the regulators at the end of the day. And so it's kind of the work of those of us in this community to be thoughtful in the way that we deploy AI tools so we don't overextend ourselves and end up proposing solutions that end up becoming either hallucinating or providing solutions that are nonsensical to subject matter experts.
I will echo what my colleague said. I think also from a research perspective is asking for assurance of quality. Recently, we're working with large language models, and if you look at how to evaluate that the large language model is doing a good job, is to use a different large language model. There should be a list that is a recipe, really, that is fully demonstrated, and as a user, you should always ask how it has been evaluated, and it needs to be evaluated on a very regular basis. The other concern that I had that I tried to convey was also for the type of decisions that we have to do, we can't necessarily use all of the data that is out there. And how to ensure that you're getting data that has been evaluated, documented at every step of the way. It's a little bit counterintuitive to open science. You also want to always challenge your research. But the stakes that we have in some of our decisions, we have to have a little bit some best practice and recommendations.
All right, thank you all. This one was originally directed towards Andrew, but anyone else can jump on this as well. Could you elaborate further on how utilities can use the results of probabilistic assessments to decide and prioritize their action plans?
Yeah, sure. I mean, effectively, it's a benefit cost framework is what regulators like. So looking at how can you maximally reduce risk and improve community safety at minimal cost. So I think it's fairly straightforward. Once you have those probabilities of failure, then you're just following a basic likelihood of event times consequence of an event is risk, which I think all utilities are very familiar with. So whoever this is, happy to chat kind of offline, but I don't know if anyone else up here has thoughts.
Okay. All right, thank you. I'll double up on you here right now. So this one also, and you touched on it in your earlier answer, physics-informed machine learning models. Could you expand upon the type of physical laws we should be incorporating into the existing ML models, especially in the context of the power industry?
Yeah, this is a tough one, I think, because this is something that I've more thought about in abstraction. It was something that I wanted to discuss with people here as well. Where I think of it is for those asset hazard combinations that are not well understood, or there's not existing models, but there's some level of constraint that we can put on there. But honestly, no. I mean, this is something that at least I have not seen being actively used yet. It's more somewhere that I think the industry is going because of the fact that we've started to incorporate these purely statistical machine learning models, and the next step would be to constrain those in some way with known physical properties of a given asset. So unfortunately, I don't have specific examples. That's just, again, where I feel the industry is going, and I think a good direction for researchers, whether within a utility or within academia, to spend some time.
Okay, yeah, go ahead.
I just want to make a comment, and even though this is not necessarily on the power grid, I'd like to provide an example of what's happening on the hydropower side. Weather forecasts have been provided with physics-based models for decades, and we are moving forward in terms of stream flow forecasts to inform hydropower with machine learning models. They are faster, so we can update the forecast more often, although it's pretty expensive to update a forecast. Update, and they are more accurate. There are a number of challenges that are associated with it. The first one is the change in business model, where typically a lot of the modeling is being done in-house. It allows for the engineers to make decisions that are important, and they know what's happening, and they know the model by heart. And when you switch to a machine learning model, typically either you build it yourself, but recently it's more companies that are selling you the forecast. And that's a dependency, that is a challenge that I believe is going to be the same if you were getting load forecast for machine learning. You were utilities, and now your load forecasts are not in-house, they are provided by somebody else. You also have a dependency that is a little bit difficult because all of your decisions is based on something that is external. So you still need to have something internal. And then those models evolve very fast. So understanding, was your model was good last year, is it going to be good next year? So there's a number, again, of the change in business model, evaluating the models every time, every year, if there is a new source of data, making sure you have transparency. So again, a lot of the best practice that need to be followed.
Okay. This came up a lot yesterday, talking about it from the grid utility side of it, but this is certainly relevant to everyone here. How might the data center and computing requirements of AI itself influence grid resilience? Who wants to start that off?
I'll jump in. So personal little fun story, I was recently participating in the Georgia IRP, and anyone who doubted load growth forecasts for data centers was tarred as someone who was anti-economic growth in the great state of Georgia. So there's a lot of positive pressure on data center load forecasts. And I think we should be honest with ourselves that utilities make money when loads go up. So there's an inherent incentive for utilities to say, you know, line goes up. And so in that sense, data centers are a opportunity for generation development, but also a big reliability risk because they are massive interconnections with very high load factors and typically very little ability to be responsive to grid conditions. But just, you know, there's a study from the Duke, you know, Nichols Center that talks about how just 20 hours a year of load curtailment can unlock several gigawatts of capacity for data centers, and that, you know, that paper's gone around a lot, very popular. And I think last week or in the last few days, Google, well, I should say, these big data center developers spend a ton of money on their chips, and they want to make their money back on those chips as fast as possible. And that means running those things to the ground as fast as possible. So there's a trade-off when they are asked to reduce their computational load. That said, I'll leave it here. Google signed a contract with a couple of utilities to provide some amount of flexibility. So they have something in their energy service agreement that says you can be curtailed up to so many hours per year at some percentage of your total load. So to me, that's a positive step forward.
Anyone want to add to that?
Maybe a small thing is also to add that this is not coming in a vacuum. So data center also require a lot of water as well. And so they have a huge impact in the whole infrastructure. And so again, those things should be looked at a holistic policy of a different state, a different community, whether they want to take on those big infrastructure projects.
Okay. This aligns with a question that I sort of had. So how can these AI models be effectively explained to the operational users and general public, and have any of these sort of systems implemented features that provide model explainability or transparency for non-technical audiences?
Yeah, I guess that's so to be slightly technical, there are two words, interpretability and explainability. They're kind of different. So interpretability is when people understand the inner working on a model, and those are more for, say, data scientists to improve and debug the models. The explainability is the layer that actually should be directed to domain experts that don't understand AI. So there is a whole subfield of that is intersect with the visualization field, where we can build dashboards that show, give users a better understanding of what, for example, the margin of error, kind of uncertainty, the variability of the results with respect to the change of the inputs. And so generally, when you build a new infrastructure, the explainability layer should be well studied and well documented and presented to the end users before they can trust properly the AI. And when I mean properly is that sometimes people trust it blindly, or they don't trust it at all because they don't understand. And it's kind of there is an interesting question of the happy medium where you use it properly, you don't discard it, but you don't go too far to take anything that comes out of the AI as if it was good.
Yeah.
So I'll go back to who is the user and what are they doing with it. We are giving model products to users who are making decisions out of it, or they're interpreting it for driving an action. If, like, when we build these systems, we start with understanding the workflow, if that exists, if the user is making a decision making with that, what that means in the context of that decision, and then build into the system interpretability and explainability of the model in a way they can make that decision. So what we are seeing a lot, especially in these new frameworks like Watcher Duty, for instance, these models are taken out of context. So the model that you, for instance, built for prediction of the fire for the next couple of hours, you shouldn't give that to public because they don't have any good decision to make with it. So over the years, this has been sort of the balancing act we had to walk through, and AI models are very similar too. Who is the decision maker and what are they doing with it? What harm they can make with it should be a part of the thinking too. So these are absolutely not transferable. That's why I'm saying what solution it goes into, who is making a decision based on that solution, and how are we democratizing that decision-making process? What I mean with it, if there is a model that gets deployed to make a decision, with everyone, can everyone with the same responsibility can take decisions and collaborate with it? Can we train them? Are they a part of the table on how that model gets to their hands from the beginning? So we are actually really giving something that's useful. So usefulness, usability are huge parts of it. So we can't separate the AI from the user and the decision-making or action of that user if we are going to talk about deploying an AI or scientific models in the societal context. So this is something, a soapbox that I've been on for a while. Thanks. Now got on it again.
Okay, we'll wrap up. You got to get out your crystal balls here, and maybe I'll start with Nathalie, and we'll go this way. So what area of AI, big data innovation do you feel will have the biggest impact in the next 5 to 10 years? So go ahead, Nathalie. This is like if you watch or listen to Wait, Don't Tell Me. This is the tail end last question. You got like 30 seconds. Okay. You're not on. Your mic.
I got it. Well, I stick to what I've been presenting today. I think that the Gen AI is very promising to provide faster analysis. So I think that, I will stick to that.
As a lot of us touched on, extreme weather, weather-dependent resources, hydro generation, particularly in the West, wildfire risk. I think all of those are becoming more and more critical for planning and operations, and I think big data, it being so big, tools like artificial intelligence will help utilities and planners make sense of that critical information.
So I think we'll see a huge change in our innovation landscape, how we are actually building solutions and innovating together. It's going to be a lot more collaborative, human-AI collaboration, but also I think the way we are creating new regulations and systems around it. So I feel like everything is changing in every industry from ground up, and this is no different.
Yeah, I mentioned this in my talk, but climate data is what I'm really excited about. The CMIP 7 is happening kind of right now. They run on a 5 to 7 year time scale, so in 5 to 10 years we'll have a new CMIP running that may incorporate some kind of AI into those models. The other thing too is I think there's just going to be stuff that we can't predict right now. I mean, the Transformers paper was what, 2017, 2019? So not even 10 years ago. So not even 10 years ago, like we didn't have any of these generative AI capabilities anywhere near what we are now. So in some sense, I think it's hard to know where we'll be in another 10 years of research.
I think one impact that people don't see quite yet is in addition to all those expert systems, the AI will help us build interface where people don't have to become expert also in using tools, programming in Python and so on. They can just interact in a natural way with the environment and still get access to high quality data that normally would take a huge amount of work. And I think that will also revolutionize many industries because so many people more can get access and use information in ways that before was kind of confined to a very set of privileged fews with lots of knowledge in a particular field.
All right, let's thank our panelists one more time here.